x to the power of 13 is equal to this, as I counted, a 26-digit number. Can we find x without using a calculator? Of course, x is a real number. So I'm going to use this Fermat's-Little theorem to help us. Right? So p is a prime number, right? X is an integer. Right? Basically, the overall plan is to perhaps use 13 to divide into this number. Right? Find out its remainder, the same remainder as x. Right? P in this case is 13. Right? So according to this logic, I'm searching for the remainder of 1. Right? Any other remainders are just useless to me. 1 is the most useful. So I want to know what's the remainder if divide 10 by 13. Mod 13. Remainder is 10. Remainder is also negative 3 as well, right? 10 minus 13, negative 3. Same idea. Right, multiply itself. 10 to the power 2, congruent to 9. 9 minus 13, negative 4. That's the remainder. I'm using the smallest absolute value here. Keep multiplying. Right, negative 4 multiplied negative 3, 12. 12 minus 13, negative 1. Like I said, I'm searching for the remainder of 1. Negative 1 is still useless to me. However, if I square both sides, I get this congruence equation. Right? Which means, yes, 10 to the power of 6, if divided by 13, I have a remainder of 1. Right? So is this going to help me? So if that's the case, that's probably, so here I have, as long as the power is a multiple of 6, it's going to be useful to me. Right? 10 to the power of 12. Also, remainder is 1. 10 to the power of 18. Same thing. That's going to be helpful. 10 to the power of 24. Right? Just as helpful. So that means I probably, because first of all, that's roughly equal to, that's 26 digits. So approximately 2.1 times 10 to the power of 24, right, roughly. So I probably have to rewrite it into a sum of, for example, 10 to the power of 24. Here's 20, so probably 21 times 10 to the power of 24 plus some other number times 10 to the power of 18. 18, that's going to be useful. After use 21, I have 24 digits left. Right? 9.8 times 10 to the power of 23. If I want to use 18, I have to move 5 places. Right? 1, 2, 3, 4, 5. I probably have to use 6 digits from here. 9, 8, 2, 1, 4, 5. Then times 10 to the power of 18. Because knowing this remainder is 1, this remainder is 1. All I need to know is to find out the remainder of this digit divided by 13. Right? But the problem is that, of course, next is probably another 6 digit times 10 to the power of 12. But you see, the problem is that there's too much calculation, right? So 6-digit number divided by 13, a lot of calculation. So luckily, it just so happens that 1001 is equal to multiple of 13. 13 times 7 by 11. Right? You can easily verify that. So if we can use 1001 as a divisor, if some number is divisible by this, it must also be divisible by 13. Right? So the benefit of using this number is that if I say 1000, what's the remainder divided by 1001? first of all, the remainder is itself, but this minus 1001, negative 1, right? Remainder is negative 1. The benefit is that square both sides. Immediately I have congruent to 1. It looks like, so 10 to the power 6, in other words. Right, so perhaps that's going to be useful. Right, so that way perhaps I can rewrite this whole thing into, let's see, so the same idea, right? So 10 to the power 12, congruent to 1. 10 to the power 18, congruent to 1. Same idea. 10 to the power 24, mod 1001. Now, every time I just raise this power 2, raise the power of 3, raise the power of 4. As long as the power is a multiple of 6, then I'm good, right? That's going to help. So which tells me that I should probably break this number into what number times 10 to the power of 24? Right, this times, so 21 times 10 to the power of 24 plus exactly the same, right? The same as this. So six digit times 10 to the power 18. Another 6 digit. Nine one 7 3 0 8 10 to the power of 12. Another 6 digit. 3 3 0 4 8 7 times 10 to the power of 6 this time. So following that, 1 2 3 4. So 1 3 3. 1 3 3 6 9. A 5-digit number times 10 to the power 0. Right? Like I said, the remainder of this is just ones. Right? Just remainder of 1, remainder of 1, remainder of 1, remainder of 1, remainder. So all I need to know is find out the remainder of this number, this number, this number, this number, this number, divided by 1001. Right? Remainder of this times 1, remainder of that times 1, remainder of this times 1, remainder of this times 1, remainder of this. So after some calculation, I found the remainder of, so using mod divisor 1001, the remainder of this turns out to be 21. 21. And the remainder of this, 164. Remainder of that, 392. Remainder of this, 157. Remainder of that, 356. That's using this as the divisor. Of course, like I said, if divided by this, the remainder, for example, of this is that. Right? Then, of course, I can obviously use divisor of mod 13. Divisor of 13. So this, don't worry, this remainder is 1, right? Just worry about this, for example. Right? So which means this can be written as a multiple of 1001 plus 164. Right? A multiple of 1001 is, of course, a multiple of 13. Right? Of course, I can divide everything by 13. Right? Multiple of 13 divided by 13. Integer, don't worry. Right? This divided by 13, right? What's its remainder? Right? This divided by 13, what's its remainder? This divided by 13. Right? So using 13 as a divisor. So 21, remainder is just 8. 164, now remainder is 8. 392, remainder is just 2. 157, remainder is 1. 356, remainder is 5. All right, so previously, like I said, if I'm using 13 as the divisor in the first place, it will be too much calculation, right? 6 digits divided by 13, too much calculation. Right now, I'm using a 4-digit number as a divisor, of course, less calculation. Worked out its remainder in terms of this as a divisor, right? But because this is a multiple of 13, right? So it's of course legitimate for me to use 13 this time, right? To further divide by 13. All right, everything else is fine. Everything else multiple of that, of multiple of 13. Don't worry, right? The essence is that these are the essence, right? Using 13 as the divisor, right? Finally, so add them all up. Turns out to be 24. Right, 24 divided by 13. Remainder is just 11, right? Mod 13. So all in all, this 26-digit number, right, break down into sum of a few digits. Right, turns out we add up each remainder. Right, add up each remainder gives us this. Right, the essence is 11. Right, the mod 13, that's its essence. So which means this x to the power 13 remainder is 11. Remainder is, like I said, Fermat, right? Fermat little theorem. So also the same as the remainder of x. Mod 13. So in other words, x, if divided by 13, it has a remainder of 11. But x cannot be too large, right? X cannot, because even though this is very large, but x cannot be too large. X, why it cannot be too large? Because x to the power of 13, roughly 2.1 times 10 to the power of 24, right? Roughly. However, it's smaller than if I replace 2.1 by 10, right? Smaller than 10 times 10 to the power of 24. That is 10 to the power of 26. X to the power of 13 is less than 10 to the power of 26. Right? If we do, so that is 100 to the power of 13. Right, 1 followed by 26 zeros. Right? So double zero times 13, 26 zeros. Same thing. X cannot be larger than 100. Right? And x has a remainder of 11 divided by 13. Right? Not too many possibilities, right? X can either be 11. 11 plus 13 is what? 24. 24 plus 13, 37. 37 plus 13, 50. 50 plus 13, 63. 60 plus 13, 76. Plus 13, 89. Plus 13, exceeding 100. So these are all the possibilities. So now these are all the possibilities because X is restricted between 0 and 100. Obviously positive, right? So let's rule out, first one I can rule out. Because 11 to the power of 2 is, last digit is 1, right? To the power of 3, last digit is also 1. So this last digit is 9. So I can immediately rule out 11. 24, right? Square it. 4 times 4, 16. The last digit is 6. 6 times 4. Last digit is 4, right? That's to the power of 3. So no matter to the power of any positive integer, I have either 4 or 6 as the last digit, right, which is different from 9. So immediately roll out. Square that. Last digit would be 9. And times itself again, so 3. So this is possible. This is possible. 50 is impossible, right? No matter, right? Last digit is always going to be 0. This is possible, right? This, 6 times 6, last digit is 6. Last digit always 6, so immediately ruled out. So the only possibility looks like 37, 63, 89. Right? So let's further analyze. So for number 36, I say, 37, I say, I want to have a look at its last digit after raised to the power of 1, for example, last digit is 7. Raised to the power of 2. Last digit is 9. Raised to the power of 3 will be 3. Raised to the power of 4 would be, last digit would be 1, right? Obviously. So raised to the power of 5. 1 times 7. 7 again. So that's it's cycle, right? 7, 9, 3, 1, 7, 9, 3, 1. So on and so forth. So the only time that the last digit is 9, right, it only appears if it's raised to the power of 2. Next cycle would be 3, 4, 5, 6, right? If raised to the power of 6, I again have, so 7 times, no, last digit is 9. So power of 2, power of 6, power of 10, right? So that's the pattern. So power 2, 6, 10, 14. That's when I have last digit is 9. Right? Last digit is 9. But that's raised to power of 13. Last digit is 9, which is impossible. Right? This is impossible. Right? So now 63, last digit. Right? Raised to power of 1, last digit 3, raised to power of 2, last digit 9, raised to power of 3, last digit is 3 times 9, 1. No, 7. So raised to power 4, 3 times 721. So last digit is 1. So raised to power 5, 3 times 3, last digit. Raised to power 6, 3 times 9, last digit. So 3971, 3971. So the pattern is that every time I raise to power of 2, 6, 10, 14, then I have the last digit is 9. Otherwise, I don't have 9, right? Cannot reach power of 13, right? Power of 13 cannot give me 9. No, so the only possibility is 89, right? Because there's no other possibilities, right? In fact, we raised last digit raised to power 1, raised to power 2, last digit 9, 9 times 9, 81, 1, raised to power 3, 9 again, raised to power 4, 9 times 9, 81, 1 again, so 9, 1, 9, 1, 9, 1, that's the pattern, right? So when do I have the last digit is 9? Every time I raised the power of 1, 3, 5, 7, 9, 11, 13, so on and so forth. I have the last digit is 9. Right? Perfectly legitimate, right?